So welcome back. So today, so far we have discussed properties of abelian group. We saw definition of abelian group, examples of abelian groups, and subgroup, quotient group. We focused on the group Z, the group Z mod nz. Now we have also learned about the group Z mod nz star. We saw direct sum of abelian group and structured theorem of finite abelian groups. We have seen Lagrange's theorem. We saw cyclic groups. And order of an element and subgroups of cyclic groups. These are the some of the topics that we studied. Now we move to the next algebraic object, which will be useful to us. So these are called rings and fields. So let us start again with the definition and some examples. Okay. So let A be a set, and there are two binary operations, plus and let's say multiplication, let's say this funny looking plus and funny looking star, be two binary operation defined on A, such that this A plus is an abelian group. Okay, so this is an abelian group, so this you already know. So so you can say this on an abelian group, there is additional structure dot or star defined on it. Further, this star is what kind of binary operation? This is associative and commutative binary operation. Okay, it is and moreover, we assume that there exists a special element identity 1a, such that a star 1a equal to 1a star a equal to a for all a in A. So this is like, so A plus, if you like plus, with respect to plus, it was an abelian group, and with respect to that, let's say the identity was 0. Now we have another binary operation, which is again associative. We are calling it, let's say, multiplication. Then with respect to that, we have an identity element. We are calling it 1a. Very soon we are just going to write it plus and dot. So we are just going to write very soon, like we'll just write plus and dot, and we are going to write 0a, the additive identity as 0, and 1a, this multiplicative identity as, 1. Okay, these are about notation. Otherwise, notation becomes too much to handle. So, and moreover, for all ABC in A, we have A times B plus C. So there is a relation between these two operations. It's called multiplication is distributive over addition. So you have A times B plus C is A times B plus A times C. And because these are associative, so these are commutative operations. So if A star 1 is A, then 1 star A is also will be equal to A. So this thing is same as, because this is a commutative operation, it's B plus C times A, which is B times A plus C times A. So yeah, so A plus B is same as A star B is same as B star A, and A star C is C star A, and then the addition is also commutative. So these two are actually same thing, because we have said this is redundant. Just for emphasizing, I'm saying this because we have already said it's a commutative operation. Then this is said to be a commutative ring with identity. Okay, so a ring means first you have an abelian group, and there is another operation defined on it. Let's say we call it multiplication of star. So that with respect to star, it is associative, commutative, and there is an identity element. Moreover, there is some relation between star and addition and multiplication, or star and plus, and this is the relation, and that the star distributes over addition. Then we call it a commutative ring with identity. So sometimes some book might have ring without the concept of identity, but we'll not deal with this. It's common to have identity. Of course, commutative again is an so A plus, it will be abelian, but with respect to this multiplication, it did not be commutative. But this is, in this course we are only going to study commutative ring. So this is specific to us. In this course we are only study commutative ring. Okay. So in this course, we'll only focus on commutative. Okay, so just like we have focused on abelian groups, we'll focus on commutative ring. So this is the definition of ring, and field is a special case of ring, a subset of like as not subset, a subclass of the like rings. So if a minus 0 and with respect to multiplication, if you remove 0, then with respect to multiplication, if it becomes a group, that is every element, non-zero element, which is, so here we should be careful. So as I said, there are two identities. Now there are two operations. There are two identities. This is the additive identity. So every element which is not equal to identity, it has a multiplicative inverse. So there exists a B such that A star B equal to, this part automatically follows because the operation is commutative. So there exists a for every A there is an element B such that A times B is identity or B equal to A inverse. Then we say that this A plus and star, this is a field. Okay. So it means A plus is an abelian group and A minus 0, if you remove the additive identity, then that set is a multiplicative group. Then we call it a field. Okay. So yeah, about notation. So this is about notation. So regarding notation, so what we are saying is that for simplicity, we'll denote the additive identity as 0 and multiplicative identity as 1. And we'll simply write this kind of plus as a plus b and a dot b, and in fact we'll just write this as ab. Okay, 2 is the notation for any commutative ring. So once we get used to, and I'll assume from now on only you're getting used to, so multiplication will write dot, and even that dot will be omitted like it is here. This a star b will be written as this dot b. There is a dot here. Even that dot will be omitted. We'll just write ab, and plus we'll just denote it by plus, where it might be some abstract operation. So example is z. The classic example, again, it will be an important example as is the set of integers. So addition we have seen, and even with respect to multiplication, it is an associative binary operation. So two integers m and n, you send it to m times n. So this is an associative commutative binary operation, with one being the multiplicative identity, but it doesn't have an inverse. So if you take 2, then inverse of 2 is 1 by 2, which doesn't, with respect to this multiplication, which doesn't belong to Z. So this is a ring, but not a field. However, if you look at the rational numbers, then rational number minus 0, every non-zero rational number a by b as an inverse b by a. So a by b into b by a equal to 1 if a by b is not equal to 0, right? So the rational numbers forms a field. Then you have the real numbers forms a field. You know this even from an analysis class. Two non-zero real number can be divided. Any non-zero real number has an inverse. And C plus complex number, even same with complex number, any non-zero complex number has an inverse. So this forms a field. So these are first one is an example of a ring, and the next three are example of a field. We'll see more examples of ring in this course, and that will be one of our focus. So let f be a field, any field, and polynomial ring in one variable over f. Okay, so next important example of ring is what is called polynomial ring. So polynomial ring in one variable over a field f. So what is the definition? So polynomial, so set of polynomial is the all polynomial expression a0 plus a1x plus anx to the power n, where ai belongs to f and f n varies. So these are just formal polynomials. Okay, so x is an indeterminate, or what it means is x doesn't satisfy any algebraic equation. So x cannot be something like root 2, or x cannot be like root 3. X, so if you write any algebraic expression, it precisely means that it's summation ai x to the power I equal to 0 if and only if each of this ai will be 0. Okay, so these are all, so x is an indeterminate, or what we call a variable. So these are just polynomial expression, formal polynomial expression, and this x is like, as I said, algebraically you can assume x to be algebraically independent element over f. I mean, there's a categorical definition, but I don't want to go into it. But you can assume x to be indeterminate, or x. So basically, it is this property which we need, that summation ai x to the power I equal to 0. A polynomial is 0 if and only if each of its coefficient is 0. So just to distinguish, these are not functions, these are polynomials. So addition is defined as component wise, a0 plus a1x plus a2x square plus anx to the power n. So x is a formal variable here, okay? X is an indeterminate, algebraically independent. So x doesn't satisfy, so it precisely means that if summation aix to the power I, oh, something happened, is 0 if and only if each of this ai is 0. This is like, you can take this definition, this is the definition of algebraically independent, and it is all such expression. And how do you add to polynomials? So you add to polynomial component wise, a0 plus a1x plus a2 plus anx to the power n, b0 plus b1x plus bnx to the power n. Their summation is, you add the constant term, you add the term of x, you add the term of x square, and so on. It goes like that, right? So whatever you have learned it already. So here one should specify this polynomial means all possible degrees allowed. So n varies. So it has element like constant f, elements of f. Then you have linear polynomials a0 plus a1x. Then you have quadratic polynomial a0 plus a1x plus x square. So you have all degree. Okay, so this n is varies. There is no restriction on number of degrees. So suppose I give you a0 and two degree of two things should not be same, need not be same. Then how do you add them? So let's say you want to add a0 plus and b0 plus b1x. So you just define a1 to be 0. So you make it a0 plus 0 into x and b0 plus b1x. So then you add them a0 plus 0, a0 plus b0 and 0 plus b1 into x. Right? That's how you add to polynomial. How do you multiply to polynomial? Well, you define multiple of x to the power n into x to the power m to be x to the power m plus n. And you define multiplication of ax to the power n, where a and b are two elements of the field, then ax to the power n into bx to the power m is ab into x to the power m plus n. Right? And then extends by distributive law. What does it mean? That if you have two polynomials ai x to the power I and bk x to the power k, then product is cl x to the power l, where the coefficient of x to the power l is summation aj and bl minus j, where j varies from 0 to l, right? So if you multiply, what will be the coefficient of constant term? Constant term will be a0 into b0. What will be the linear term, coefficient of x? It will be a0 into b1 plus a1 into b0. What will be the coefficient of x square? It will be a0 into b2 plus a2 into b0 plus a1 into b1. So like that. Okay, that's what it is written. So that's how the multiplication of two polynomial is defined, and this is how the addition is defined. So you can, and if you have polynomial a0 plus, this is like a definition. So the degree of this is defined to be n. So if you have a polynomial a0 plus a1x plus, so maybe I should put this in bracket, definition of degree of a polynomial. So if it is a constant polynomial, then the degree is 0. If it is a linear polynomial, degree is 1. If it is a quadratic polynomial, then the degree is 2. If it is a cubic polynomial, degree is 3, and so on. Okay. And anyway, so with respect to this group, with respect to this addition, why it is a group? Well, it has the identity element. What is the identity element? 0, the 0 polynomial. 0 polynomial means each coefficient is 0. And what is the multiplicative identity? Multiplicative identity is the constant polynomial 1. So 1 plus 0 into x plus 0 into x square, we can think like that. So that is the constant polynomial 1. So that is the multiplicative identity. And associativity with respect to both the operation holds, commutativity with respect to both the operation holds. Inverse, additive inverse of a polynomial a0 plus a1x plus a2x square plus anx to the power n is minus a0 minus a1x minus a2x square minus anx to the power n. So every element has an additive inverse, and this is not a field because x, for example, maybe I should write it somewhere. This is not a field because x is not invertible here, right? So if x, so let's say if, so let me write it here. If x into f of x equal to 1, that means you get x into fx minus 1 is equal to 0, right? That means x satisfies polynomial over but that is the definition where fx is not equal to 0, right? So x satisfies a polynomial, but this is contradiction to this, right? So that's not possible. X is algebraically independent, so x cannot satisfy this. So this is a contradiction, so this is not a field. So fx not a field. Okay, so yeah, so this is what is special about field here. We have not actually used, so this will be more useful to us. So I started with this example where f is a field. So for example, f could be equal to q, f could be equal to r, f could be equal to c. So there are several examples, and we'll see more examples of it. Okay, so we'll see more examples of it. So, uh, so in fact, we can take any commutative ring A with identity A. We can take any commutative ring, right? And then you take any commutative ring, then if I take any commutative ring A, then AX is a polynomial ring in one variable over A, right? And how is it defined? It's the same way. You take all polynomial expression in this, and x where x is the indeterminate, then this is a polynomial ring in one. X doesn't satisfy any relation over A. X is algebraically independent over A, indeterminate over A. Uh, then this is called this is the one variable polynomial ring over A, defined in the same way. Now, once we define polynomial ring one variable over A, so this is a ring. So you can think this Ax equal to B, and then you can define polynomial ring over B, By, right? So Ax of Y, so you define polynomial ring in two variable over ring A to be the polynomial ring one variable, and then over that you take one more variable, right? So similarly, we can define inductively n variable polynomial ring over any commutative ring with identity. So I first define polynomial ring over a field because that's we'll see that has special property, and that's some sense easier and will appear more often for us. But any ring Ax, we can define polynomial ring in one variable over it. For example, we can define Zx, right? Polynomial ring over Z. Or we can define a polynomial ring over Z mod nz x. Right? We can define, let's say, Z mod 6Z. We have a ring, and polynomial ring over that we can define, for example, right? So, and if you have a polynomial ring on one variable, we can call that ring B, and we can define a polynomial ring over that in one variable. So that gives you, this is the definition of polynomial ring in two variable, for example. And similarly, we can define polynomial ring in many variables over ring A. So these are some of the examples of rings. Now let us see one more example. We had the cyclic group Z mod nz with respect to addition. And now we can define another operation on it. Okay, so what is the operation? So A dot B equal to A times B. Okay, class of A times class of B. So A is in Z mod nz. A belongs to Z mod nz. And B belongs to Z mod nz. Then you define A dot B, multiplication of this, to be equal to the class of equivalence class of AB with respect to this relation over this. So we have seen this is a well-defined. So we have seen this operation is a well-defined commutative associative binary operation with the identity element to be equal to 1, right? So when I gave example of Z mod and Z star, we have discussed this, that this multiplication is well-defined. So if class of A equal to class of C, and if class of A is equal to class of C, and class of B equal to class of D, then we have seen this is nothing but class of CD, right? So we have seen this in a previous class. So that means this is a well-defined binary operation, and clearly one is the identity, multiplicative identity. So this forms a ring. Further, we have seen, for example, n equal to 4 and n equal to 6. This is not a field. Okay, so this is the example of a ring which may or may not, which may not always be a field. However, One special case it will be. So I asked last one of the previous class. I asked you that what happens for a prime p. So let us assume that m equal to p a prime. Then z mod pz star, the a in z mod pz such that a is co-prime to p. So so if we take n to be equal to a prime p, let's say p equal to, for example, n equal to 7, let's say, then what do you see that so for example n equal to 7, then z mod pz star, those elements. So we saw that this forms a group. Every element here in this subset of z mod nz, z mod nz star, which is those classes in z mod nz, so that which are co-prime to n. So here n equal to prime, so it is those classes which are co-prime to prime. But then it comprises of every classes 1 to up to p minus 1 except 0. So this is nothing but z mod pz minus the class of 0, right? It is every class except 0. So, and this forms a group. We have seen it in the previous class. So that means z mod pz minus 0 with respect to multiplication is an abelian group. So that means by definition z mod pz plus and dot, this is a field for any prime p. So this is an example of a what is called a field. Okay, so z mod nz is a ring, and if uh, p is a prime n equal to p, then z mod pz is a field. Okay, so this is another example of field. So this is a field with finitely many elements. How many elements? P elements, 0 up to p minus 1. So this finite field is p element is often denoted by fp. Okay, so here we see another thing that uh, okay, so this is a finite field, and this is also denoted by fp. So here okay, so here we see that if we add an element p times, so if you have like an element here in fp equal to z mod pz, I'm denoting an element, any element here x, right? Then if I add x plus x plus x p times, right? Then this is 0, where 0 is the additive identity of this field. So and so and so for this is for any x, for all x. Okay, so p times x equal to 0. On the other hand, if I take some other field like x equal to, if I take x in q, right? Then if I take any p times x or any n times x, if I add, and x is not equal to 0, of course, then if I take n times x, then this is also not equal to 0 for any n in n. So this raises this definition. The characteristic of a field. So in particular, okay, so even before going to this definition, we see that in particular, here we see that p times 1 equal to 0, and here we see that p times we see that n times 1 is not equal to 0 for any n in n. Okay, so this one is in fp, and this one is in q, right? This is happening in q. So sometime some field what can happen is that if I add the if I keep adding the multiplicative identity, then after some stage I might get to be, it is to be equal to 0. Other fields we get it is never is equal to 0. Okay, so this prompts this definition that definition the characteristic of a field is the smallest positive integer integer n if it exists, provided it exists such that n times 1 equal to 0. If there is no such integer, then we say characteristic of a field is equal to 0. Okay. So here, let us be clear what is the meaning of this. Okay, let's make sure that there is no confusion. What is the meaning of n times 1 equal to 0? Here it means 1 plus 1 plus 1. You add, this is the one field f, let's say 1f plus 1f plus 1f. It means the multiplicative identity if you add n times in the field, then you get the additive identity of the field. If such an n positive integer n exists, then you call the characteristic of the field to be equal to n. If no such thing exists, so for example, I give you the example, you take f equal to z mod 7z, let's say, right? So that is a field because 7 is a prime number. Then you add what is the 1f? Here, 1f is the equivalence class of 1 modulo defined by the relation the two integers are um, related if and only if their difference is divisible by 7, right? So if you add this one 7 times, then you get 7 into 1, which is the class of 7, which is the class of 0, which is the additive identity here in z mod 7z. So here the integer is 7, and you can see there is no smaller integer works. On the other hand, for q, what is the 1 of q? It's just the natural number 1. And if you add it n times for any n times, then you get simply equal to n. Okay. So, and that is equal to 0 of q means it's actually 0. So n is never equal to 0. So no such integer exists. So characteristic of q equal to 0, characteristic of z mod pz equal to p a prime. Okay. Now, one of the exercise we can do is that, so characteristic, so we'll do this exercise that characteristic of a field is either 0 or prime number. It cannot be anything else. So we saw example where the characteristic is 0, for example q. Similarly, you can say r. Similarly, you can say c. This is all fields have characteristic 0. On the other hand, we saw z mod 7z as characteristic 7. Any z mod pz has characteristic p. And these are the only possibility. It's not possible some field has characteristic 6. Okay. So yeah, we'll see why that is the case. Yeah, maybe we'll see it next time. Okay, thank you, and we'll meet again.